So yes, so we said this small piece of code will be the skeleton. So now I'll go through every aspect of this, explain what it is, the concepts behind it, why we're doing it, and the other things we might want to consider when we're choosing values for these arguments. So first, we're going to focus on this outer sample validation. So here we use this leave group out cross validation. So because the aim of machine learning is to predict data and to predict new data, really this whole idea of pulling data out and using it as test data is driven by the fact that that is what the models are for, and therefore that to know how well our models are doing, that is what we have to do. So it's kind of quite a conceptual reason for doing it. There's also practical reasons that we'll cover a bit later, but the driving force behind doing this is that if our claim our models are good at predicting new data, we have to show that, and the only way we can do that is by holding out some of our data. So yeah, I showed a simple leave group out cross validation where we just pulled out 25% of the data. That's one common sort of method for splitting the data. Especially if you have smaller data, what you might want to do is called k-fold cross validation, where you split the data into, say, 5 groups. For k equals 5, split it into 5 groups, and then we'll use each group in turn as our holdout data. So we'll use the group of data, group 1 as the holdout, and train or fit our models to groups 2 to 4. And then we'll use group 2 as our holdout and fit on groups 1, 3, 4, and 5 all the way through. So you end up fitting the model 5 times at least, but it means that each of your data points are in the holdout set at least once. So particularly if you've got a smaller data set, you might have 1 or 2 kind of awkward data points that are particularly hard to predict. And if they're never in the holdout data set, you'll kind of think you're doing a bit better than you are in terms of how good at predicting your model is. Relatedly, and kind of best practice really, is this repeated k-fold. So we do k-fold cross validation, and then we do it again with a new random splitting of the data. So we'll split the data into 5 random chunks, run the model 5 times, then split the data into 5 different random chunks and run the model 5 more times, and maybe do that whole process 3 or more times. So this sort of is the same idea that you want all the data points to be in the holdout data set at least once, but also if you've got, say, 2 tricky data points that you want to be in the holdout data set together at the same time, this gives you more chance of kind of capturing those clumps of data that become difficult to predict in the holdout data. And it kind of gives you, so like this k-fold, you could see it's kind of, you've got 5 estimates for your out of sample predictive ability. Doing it this way, you then might get 15 or 25 sort of data points for how good your model is at predicting. So if we're doing things really properly, we'll sort of have a central estimate for our predictive performance and some uncertainty around that. And so kind of the more kind of times you can split up your data, the kind of smaller your uncertainty intervals on that predictive performance you'll get. And then a final message for here is bootstrap. So you take your data set, you sample, if it's got n rows set, you sample n rows with replacement, and that will mean that some data points are in your training set twice or more than twice, and some data sets are not in your training set, and those ones end up being your test set. So you end up with about 30% being held out. From my understanding, it's basically just not as good as k-fold cross validation, but it comes up quite commonly, so it's worth knowing about. And it tends to be a little bit optimistic of how good at predicting your model is. So as far as I understand, there's no real reason to ever use this over repeated k-fold cross validation, but it's worth knowing about. And it's worth just sort of being clear about, because sometimes in statistics, for example, we can use bootstrapping as a way of getting uncertainty around an estimate. So you fit the mean, and then resample the data a bunch of times and fit the mean each time, and that gives you like a distribution. So it's kind of the same idea of sampling the data, but you're using it for a very different reason. So it's worth just being explicit about what we are and aren't doing here. But ultimately, it's the same idea of using some data in your training set to fit the model to, and some data separately that you then test how good your predictions are. So a big problem with all those methods I just mentioned is that they all assume that your data are IID and that they're sort of IID sampled individually and identically distributed, and individually and identically distributed from the population that you actually care about. So ultimately, if you're using patients, for example, you're assuming that those patients are completely randomly sampled from the full population of people that you're interested in. And that's often not true. So we need to be really careful about this, and there are ways to try and sort of adjust our estimates of how good our models are by using different techniques. So instead of splitting the data into 5 or into 2, if we've got, say, 2 separate cohort studies, a really good thing to do is train your models on one cohort study and then test them on the other, and then do the other way around as well. And that way, any biases in those cohort studies, there might be biases in who's selected for the cohort study, or there might be biases in just how the measurements are made, or like differences in between the studies and how the measurements are made. Those the sort of the loss of performance that you receive due to those biases will become apparent because you're using a completely separate set of data without those biases, or with a different set of biases, to test how good your model is. So this can be really powerful. If our data are very spatially kind of embedded in space, like a lot of our data is, I think in this department, you can do spatial cross-validation, where you, for example, you split the data into 5 spatial clumps. So do like k-means clustering on the locations of the data, or perhaps like a grid, and say like, hold this whole block out. And that's testing a bunch of things. So for example, if people in different areas are, the relationships between covariates and response variables are very different in different areas, this will start highlighting how your model performance degrades as that in the presence of that. And one particular application is if you're using space as a covariate. So for similarly to kind of any spatial regression, if people have done those, if what you want to do with your model is predict people far away, you then can't use that spatial information very well. So you might want to do spatial cross-validation to say, well, this is how good my model would do at prediction if I'm predicting someone far from a different place to where my data was collected. It's the same idea with temporal cross-validation. So forecasting is very much in the news as we all try and guess how bad winter's going to be. If we're sort of making forecasts in the real world, the very kind of obvious thing is we don't have any data from the future, or we don't have any covariates from the future. So if we want to test how good our model is at predicting the future, what we should do is, say, use the first 10 years of our data and then try and predict the last year or predict the last 2 years as the holdout. And and if you want to sort of have kind of more related to k-fold, you might use the first 8 years and predict the years 9 and 10, then use the first 10 years and predict years 11 and 12. So again, it's putting that temporal structure back into our cross-validation scheme to try and capture some of the loss of predictive performance we would get. So machine learning models, we'll see this a little bit later, hopefully if we've got time. One thing machine learning models tend to be quite bad at is extrapolating beyond the range of the data. And so if a core part of your research question was, how good is my model at predicting outside the range of my data, outside of in different areas of covariate space to the data that I do have, what we might want to do is split the data up by covariates in some way. have a split along the covariate of interest, for example, and say we'll use all this data that's below age of 50, say, and then try and predict everyone whose age is above 50 and see how terribly our model does because it was so reliant on having everyone the same age, for example. So the thing here is that your cross-validation scheme, your validation scheme, should be entirely driven by the questions you're asking, and it should be entirely driven by the structure in your data. And so I would say this is like the most important part of any machine learning analysis is deciding how to do this and deciding how to do this well. And sort of in the same way that any statistics lecturer will bang on about this stuff for hours and hours, it's the same in machine learning. You need to capture that structure in your data and sort of account for it in the cross-validation scheme. Otherwise, you're going to be overly optimistic as to how good at prediction your model is. So then a last part to this is if we're testing lots of models, then if we're testing lots and lots of models, some of our models will do well on the holdout data just by chance, not because they're really effective models. And so part of this, we can say that selecting the model is part of the model. And so if this is kind of an important consideration, or if a really truly unbiased estimate of how effective our model is an important part of our analysis, what you should tend to do is what's called Autocross validation. So we have, we'll sort of compare a bunch of models with a cross-validation scheme like we just discussed, but then we'll have an extra held out data set that never gets used by any of these models, and we'll only test like one or two models on that final data set. So sometimes called train, test, validate. So the simplest scheme is to split the data into three: one large chunk for model training, for fitting the model, a large chunk for fitting many models to, a small chunk for testing all those many models to see how well to compare between them and choose like one or two best models at the end, and then a third chunk that only the best two models get tested on. And again, this should be driven by a question, and sort of, yeah, it can be really important, or if depending on your question, it can be less important. And annoyingly, it's not done automatically for you by caret, so you have to do it manually.